Hello everyone, my name is Judy and today I'd like to talk about quality of service provisioning mechanisms for fog computing networks. This is the topic of my PhD thesis, which is part of the Big Cloud project, so let's start. More data is being created in more locations than ever before. Internet applications running on IoT, mobile, and end-user devices generate a massive amount of data. However, data by itself is not useful unless it is processed to obtain information. In the traditional model of connectivity, all generated data were transmitted to a cloud for processing. However, this method has serious drawbacks such as security, the location and cost of data, scale, and speed. Fog computing overcomes these limitations by distributing computation, communication, and storage services along to the cloud-to-things continuum, empowering potential new applications such as smart cities, augmented reality, and virtual reality. Fog nodes located at the edge of the network are usually limited in resources, but their use involves only brief delays in communication. On the other hand, the cloud has a large number of resources but involves long delays in communication. Thus, the integration of fog and cloud computational resources is necessary and introduces new challenges in resource management. The major challenge in a cloud fog system is to decide where applications should be executed, whether on the cloud, on the fog, or in the end-user devices. To this end, the scheduler must consider input variables related to the application, such as resource demands and the quality of server requirements, as well as variables related to the availability of resources. In this context, one major question is how to map the quality of server requirements of applications on cloud and fog resources. One possible approach is to discriminate the applications arriving at the fog into classes of service according to their quality of server requirements. This mechanism allows to carry thousands of different applications, is flexible, scalable, and does not require signaling. The first step to implement the service differentiation strategy was the definition of classes of service for fog computing. To this end, 9 quality of server requirements were considered: bandwidth, reliability, security, availability, data location, mobility, scalability, delay sensitivity, and loss sensitivity. Based on these requirements, 7 classes of service were defined: mission critical, real-time, interactive, conversational, streaming, CPU-bound, and best effort. Besides, a priority level was assigned for each class of service for potential adoption in scheduling systems. Also, the range of quality of service requirement values for each class of service was established. After defining the classes of service, a methodology for choosing and evaluating classifiers for fog computing application was proposed. The first step is the creation of a labeled dataset containing quality of service attributes of fog applications, which can be either real or synthetic. After that, the value of the different quality of service attributes should be preprocessed. Classification techniques based on machine learning can then be applied. To check the robustness of a classifier, a copy of the original dataset should be contaminated by the introduction of noise at different levels. The performance of the classifier should be assessed by a performance evaluation process which encompasses both the measurement of performance and the result of a statistical test. At this point, the classification model is ready to receive new inputs for scoring. The new data, however, must also be subject to a preprocessing process. After all these steps, the classification model can be integrated into the cloud fog system as a new network element. So this figure shows how the end user submit applications to be processed on a cloud fog system. A classifier at the network edge labels the application. The label identifies the class of service of the application. After that, the class of service and the workflow of the application are forwarded to the scheduler, which maps each task of the application onto available Cloud Fog nodes. This table shows a mapping between the proposed classes of service and the processing layers of the Cloud Fog architecture. These charts present accuracy results and testing time for the classifiers used to identify the class of service of the application running at the edge of the network. Different algorithms based on machine learning were evaluated for potential adoption, such as adaptive neural-fuzzy models, decision trees, neural networks, k-nearest networks, and support vector machines. All these techniques were implemented with clean and noise datasets. Some experiments were also made where the scheduler receives the application with the class label. In this stage, two schedulers were proposed. One solves an exact integer programming formulation, while the other solves a relaxed version of the problem based on an approximation algorithm. These are some publications about this work. Thank you for watching my presentation. If you require any further information, feel free to contact me via email at jguevara@lrc.ic.unicam.br. And don't forget to visit our website, bcloud.ic.unicam.br.